start. Sorry.
No worries. All right, so it is 4 o'clock on Sunday, November 28th. It is technically the Sunday of fall break, but also technically not because of how fall break works exactly. Regardless, everybody is slowly coming out of break time and getting back into gear. So it's time to talk about your exam 5. I know everyone's excited. So couple of things. So exam 5. I know we had a break, so therefore everyone's forgotten how we do all of this jazz. So let's just start from the beginning. So exam 5 is on Saturday, December 4th at 10 a.m. You need to be into the exam between, I'm going to say between 10 a.m. And 10:15, because while yes, that exam window is open a little bit longer than that, technically until 10:30, if your clock says 10:30, but eLearning's clock says 10:31, you are out of luck. So just aim to be in there between 10 and 10:15. That way, if you suddenly realize that your calculator is across the room or your laptop charger is in your car, you have time to go and get it. I apologize if you can hear my dog in the background who has seasonal allergies and maybe coughing in the background. Hopefully you can't hear that too much, but that is coming up in about, what, 6 days? So that is coming up very, very soon. Exam 5 covers, I'm just going to call this chapter 10 and chapter 11. So technically this is the chapter 10 that we didn't already test on. So technically this is supposed to be 10.4 to the end. I apologize. I don't remember how many sections are in chapter 10. But the tricky thing with this is that a lot of the things that you need were in those beginning sections. So oftentimes we talk about what things do you still need to remember. And the hard thing is that there's a lot of stuff in that 10.1 to 10.3 that's still really useful, like the first law of thermodynamics, which said that energy can be neither created nor destroyed, just transferred. We're still using that information. We talked about the definition of the change in enthalpy in those beginning parts. We also talked about how to manipulate thermochemical equations, which is definitely something we use in Hess's law. So they're thermochemical equations. So the difficult thing, while technically exam 5 does not include 10.1 to 10.3, honestly, in reality, it does, because those introductory sections have a lot of information that we still need in order to do the rest of the chapter. So while there are some things that we won't ask you about because we've already had our opportunity to do so, things like work and heat, that was back in that first law stuff, that stuff's over. Some of the manipulations that involved working with enthalpy and stoichiometry, that stuff's already over. The hard thing is that more of the stuff comes forward. Oh, state functions. State functions are still a thing. That still winds up being important because that's also how Hess's law works. Yeah. So anyway, I'm just going to call this chapter 10 and chapter 11 because honestly, you need it all. I'm just going to say all of it because you need most of chapter 10 to get in there. And chapter 11, this is actually going to be all of chapter 11. Chapter 11 is the gases chapter. So a lot of people remember from high school this equation of PV equals nRT. And that is what a lot of chapter 11 involves. So in my mind, chapter 11 has 3 parts. It's got concepts. It's got dealing with PV equals nRT, as well as dealing with this rearrangement of PV equals nRT, where we can talk about the fact that, hey, I could put everything equal to R, and if everything was equal to R, I would actually have a second set. And I could therefore look at a variety of different gas laws by using this thing, by using P1 V1 over N1 T1 equal to P2 V2 into T2. For those of you who haven't seen this before, P is for pressure, V is for volume, N is for number of moles. T is the temperature in Kelvin. Very important, by the way, that this is in Kelvin. And R is the gas constant. The gas constant has a lot of different possibilities. So depending on where you've seen it before, what units you've seen it before, you may have seen it in a variety of different things. The gas constant we're going to give you is going to be this one, 08206, and this is in liters, atmospheres, moles, Kelvin. So anytime you're using this gas constant, your units have to match. The last thing to mention about generalities with the upcoming exam, we are still going to be aiming for somewhere between 27 to 32 questions, somewhere in there. I won't know until we finish writing the exam. As usual, I haven't started writing my exam questions yet. Been thinking about them a little bit, but haven't actually written them. The last thing to mention while I've got your attention a little bit is the fact that you have a final exam. So we don't actually do exam reviews for the final. This, frankly, is because you've already seen the fact that in 2 hours, I can't even cover the amount of stuff that's on one exam. The final exam is cumulative. And there's really no way in 2 hours to do a final exam review that makes anybody happy, because there's so much stuff and I can't cover everything that's on a single exam in 2 hours, let alone covering a smattering of all the topics that would be on the final. So essentially 2 hours of a miscellaneous set of random topics just tends to make people frustrated. So we just don't do final exam reviews. But your final exam, it is cumulative. I'm going to tell you that it's chapters 1 to chapter 12. So we are still going to cover chapter 12, even though chapter 12 is not on exam 5. So chapter 12 is on the final. It's not on exam 5, but it is on the final. Chapter 12 is very short, by the way. I'm going to go ahead and say chapter 1. There's not a lot of stuff in chapter 1, but again, kind of covers my bases because there's a few odds and ends in chapter 1. The other thing with the final to keep in mind is it is on Saturday, December 11th. It is at 8 p.m. So this is in the evening. It is a different time. The registrar's office gives us this time slot. We do not pick it. We are told by the university when this is. And it goes for 2 hours and 45 minutes. So I understand that folks are usually not happy with anything that has to do with the final, but as far as its timing, that is all up to the registrar's office. That's not a decision that they ever even ask us for input on, by the way. They just tell us when our time slot is. But it is cumulative, so it is going to be over chapters 1 through 12. And it is Saturday, December 11th. So yes, that is roughly 1 week in between your 5th exam is the final. For those of y'all that have not looked at a calendar yet, be aware that where we sit right now, just in case you're curious, is there is today, which I realize you guys may not be watching this on the same day, but today is Sunday, November 28th. We then have a week of class, and then Saturday, December 4th is your exam. And then there's going to be next week, Sunday, December 5th. Then Monday and Tuesday, we have classes. So we do have class the Monday after your exam. Then Wednesday is something, if you're new to this university, you may not have heard of before. It's called Reading Day. It is where there are no classes, there are no finals. Everyone is supposed to hang out and study. So that's Reading Day. Reading Day is the day of nothingness. And then technically Thursday through the following whenever is when finals start, finals week. And that's where Saturday, so our final exam, for the record, is smack dab in the middle of finals week. So Saturday, December 11th, 8 p.m. Is the final. Exam 5 is at 10 a.m. Your final exam is at 8 p.m. So just to kind of give you guys a little bit of a bird's eye view of where we're headed, the end of the semester is coming up really, really quickly. So this is always the oddity that comes along with fall break, which is the fact that once we come back from fall break, the end of the semester is really, really close by. But yeah, so that's just take a look at the calendar and realize that we are almost to the end. The other thing that I will not go into great detail on here, but if you guys have not seen the announcement, do make sure you're checking the announcement section in the 701. If I click back over here. Yes, I was looking at the chapter 10 key, by the way, is for your homework. So for everybody who got excited that it said something about a key, that's the chapter 10 end of chapter questions that I have that are posted on all of y'all's pages. It's not something new. Oh, in the announcement section, there is of course an announcement about this exam review. There's also an announcement about how ALEKS scores will be determined for the semester. So please do read this, take a look at it. If you have questions, go ahead and ask your instructor. But if you haven't actually read this announcement yet, please do read it and figure out what's going on. Because we are changing things up a little bit about how we're going to take care of ALEKS at the end of the semester. Okay. So I'm done with administrative stuff. It's almost 4:15. Any questions so far?
We have only gotten one. It says, is chapter 10.8 section of lattice energy in the exam at all?
Oh, so lattice energy is essentially another extension of Hess's law. So it's really just another example of how to use Hess's law. We typically don't actually test on any specific examples of lattice energy, essentially because it's just another version of Hess's law. So thank you, I forgot about that. Because yeah, I never talk about lattice energy explicitly, and it's just another version of Hess's law. So excellent question, and yeah, we don't actually test on lattice energy at this stage. Okay, cool. So speaking of Hess's law, so there weren't any questions that people had when we got all of this stuff started. So therefore, I had to make up my own. So what we're going to do is look at the miscellaneous questions that I came up with. And since I'm already out of space, I'm just going to add another page and put my stuff over here to make my life a little easier. Also, that way I can make my font bigger. And hope this doesn't mess too many things up. So basically what I thought I would do, since people didn't submit questions ahead of time, is I basically made up a miscellaneous group of questions. So it will not really represent everything in its entirety, but I'm also going to, unless people stop and ask questions, I'm actually going to bounce back and forth between chapter 10 and chapter 11 to try to showcase how I would know which chapter those questions are from. So this one has some little equation up at the top, and it says calculate delta H for the above reaction given the reactions below. And these are not lined up nearly as prettily as I'd hoped, but these all have some sort of chemical reaction and something about a delta H in kilojoules per mole. So the beautiful thing about having chapter 10 and chapter 11 on the same exam is this is the change in enthalpy. And that is going to be chapter 10. So enthalpy questions are going to involve thermodynamics, which is all chapter 10. So even though both chapter 10 and chapter 11 can have chemical reactions in them, you're likely going to see, hey, if it's asking you about delta H, that's a chapter 10 kind of question. Now, the next stage is that since I want to calculate delta H, there were actually 3 different ways to calculate delta H. And those 3 different ways were to use Hess's Law, where we basically manipulate thermochemical equations and then add up all of the values of delta H. There was looking at the standard enthalpy of formation reactions, which you might remember is the one where we're looking at products minus reactants. And then the last one was bond enthalpies. And yes, I do have an example of each one of these. So essentially, since what I have here, they are giving me a bunch of information, but in the information that they gave me, I don't actually have delta H of formation reactions. I know that because a delta H of formation reactions is very specific in that it has to have 1 mole of the product. Now, technically, this is 1 mole of a product, and this is 1 mole of a product, but this one's not. So this one is definitely not a delta H of formation reaction because it's not looking at standard, at 1 mole of the product created. So we are definitely not using delta H of formation reactions. Also, usually we're pretty good, and usually we would have told you that they were delta H of formation reactions in the table. And then bond enthalpies, if it was bond enthalpies, I would have a table that would talk about carbon to carbon bonds or chlorine to chlorine bonds or hydrogen to chlorine bonds. I would have a table that would have information about bonds. And that's not what this is either. So in part through process of elimination, this is going to be a Hess's Law question. So what I'm going to do is I'm going to manipulate these equations, add them all together to get this reaction here at the top. So this top reaction is my goal. So this is the goal. What I'm going to do is I'm basically going to start with at the top, and I'm going to try to go just from left to right. So the first thing I'm looking for is I'm looking for 2A, and I only have 1 equation that has A in it. And when I look at that, what I can see is that I want 2A, but I only have a reaction that has 1. So what I am going to go ahead and do is I'm going to go ahead and multiply everything in that first reaction by 2. So this is actually going to be 2A plus 2D yields 2F. Since I multiplied all of those by 2, I also need to multiply my value of delta H by 2 as well. So this then becomes 40.2. So I've got my 2A. The next thing I need is I need B. I only see B in one place. That makes my life a little easier. And there it is. B is on the left-hand side of the reaction, which is exactly where I need it. It's got a whole bunch of extra stuff I don't need. I am going to cross my fingers that everything cancels out in the end and I don't have to do anything. That's going to be my general strategy when there's a whole bunch of extra stuff that I do not want, because I need B and it's only in one place. So I'm going to go ahead and copy this down exactly as it is because I need just 1 B and I need it on the left-hand side of the reaction. So I'm just going to hope that everything magically cancels out in the end. I'm just going to copy everything exactly as it is. And then the last thing I need is I need C. And again, this is only in one place. But now I can see it's got 2 problems. One, in the reaction that's given to me, I have 2C and I only need 1. It's also on the wrong side of the equation. So I actually have to do 2 things here. I have to essentially either multiply everything by 1/2 or divide everything by 2, however you want to think about it. And I also need to flip everything. So everything that was a reactant is going to become a product. So I'm going to have 2D plus 2C, except I'm going to also change my coefficients on here. I just want one of those, and that means I'm also only going to have 1/2 of E. And as a result, my delta H value needs to be cut in half as well. So this is going to be 21.45. I'm going to hang on to those extra digits for dealing with rounding. So I have everything. I've gone through. I think I've gotten everything I've needed. Now I need to cancel things that are the same on both sides. So I'm going to get rid of this 1/2 E because luckily I have 1/2 E here and I have 1/2 E here. So both of those will cancel. Then this business with the 2 F's, those also cancel. So I can just get rid of those guys. And the other thing I can also cancel is I have 2D over here. So there's 2 of them. And here's one, and here's the other one. So essentially anything that's happening on either side of the equation, I can go ahead and cancel. It's a lot like how we got rid of spectator ions back in chapter 9 when we were going from the ionic to the net ionic equation. Anything that was on both sides of the reaction arrow with the same state symbols in the exact same form, we could get rid of. I realize here I'm just using A's and B's. It's the same general idea that way I can get rid of extra things I don't want. So then in the end, I have 2A plus B yields C. And then essentially, oh, this was supposed to be a negative sign. Sorry, this was reversed. So that 21.45 also was supposed to be negative. Negative 21.45. There we go. So essentially all I'm going to do now is add together all of my values of delta H. So a positive 40 plus a positive 11.5 plus a negative 21.45 gets me in the end a positive 30.25. My value of delta H, my units should match. So this is in kilojoules per mole before. So this is still in kilojoules per mole. And I do want to just take a moment to double check that my equation matches. 2A plus B goes to C, and there's my 2A plus B goes to C. So Hess's law is one that does require practice on your part to be familiar with balancing thermochemical equations. If you're going to reverse things, make sure that you flip the sign on them, like I almost forgot to do. And then in the end, it really is just adding everything all up together. So do take a look at some of those end of chapter questions because they do have some practice Hess's law questions in there. So what's next? So we're going to take this question next. As before, oh yes.
There was this one question which said, would calorimetry be also another method to calculate delta H?
So calorimetry, yes. So calorimetry is another method to calculate your enthalpy value. So as long as you have the correct amount of information. So yes, you're absolutely right. We'll just go ahead and add that one to the list because you can definitely get it from calorimetry. Yes. Other questions?
There was one other that they were asking, wouldn't the third part be negative 21.45 since you swapped the sides?
Yes, and I went back and corrected that because
Sweet.
So
no more questions then.
So a lot of times you see the calorimetry used where you have things like looking at either dissolving something in solution, or there are problems where you can actually have, say, an acid-base reaction reacting, and you can measure the change in temperature and get information about enthalpy that way. The reason why we talk about calorimetry as being an option for delta H is because your value of enthalpy, if you'll remember, that change in enthalpy is actually the same as your value of heat at constant pressure. That was also back from those earlier sections, that 10.1, 10.2, 10.3, somewhere in there. We talked about the fact that your enthalpy was essentially equal to your heat at constant pressure. So yes, calorimetry is also another way to look for enthalpy. Okay. So next question. A 27.1 liter gas cylinder containing nitrogen N2 holds 4 atmospheres of pressure. If the same cylinder was only 15 liters, what would the new pressure be? This question, one, says gas cylinder, super helpful, and it has information about pressure. And it also has information about volume. This is going to be a chapter 11 kind of question. And as we look at this, different people have different ways to think through what are we going to do. But what I like to think through is what I have information about liters. So that's a volume. And it tells me that there's a pressure associated with that particular volume. So a 27.1 liter gas cylinder containing nitrogen and holds 4 atmospheres of pressure. So that's one sentence all by itself. So therefore, I have information about a volume and a pressure that's all together in that one sentence. If is going to be some sort of change oftentimes. If the same cylinder was only holding 15 liters, so in my if scenario, my volume is 15 liters, what would the new pressure be? As far as things like what kind of equation do you need? There are 2 schools of thought. And so this is one of those times where I can't tell you how many equations are on the exam because I think there's only one. So for me personally, I find it a lot easier to deal with the ideal gas law or ideal gas equation, which looks like this, and then rearrange this so that it can all be equal to the gas constant, which means I can have the second set. Then from here, what I can do is this is a gas cylinder, and the gas cylinder doesn't give me any information about moles of gas. So I'm going to assume it's going to be the same because it's one gas cylinder and all we're doing is changing the volume. That's the only thing that we're doing. So we're essentially keeping the number of moles constant. And also doesn't tell me anything about the temperature. So I'm going to assume that my temperature is also the same. And if it makes you feel better to put in a value there, you can just assume whatever you want because essentially we're saying that nothing's changing. So once I get rid of all of those, the equation I wind up with is P1 V1 equals P2 V2. Now, so that's how I would do this, is I would have my ideal gas equation, set everything equal to R, and then say, okay, I don't actually need all 4 variables because there's nothing about moles, there's nothing about temperature. I just need pressure and volume. Let me just get those. That's how I would do this. Other people prefer to have a list of equations. So for people who prefer to have a list of equations, you may actually recognize this equation here as being Boyle's law, which is the one that just deals with pressure and volume. So you might recognize it that way. You might just know the combined one and then get rid of the things that you don't need. Either way will work for this particular equation. So what I am then going to do, okay, I've got my question, I got all of my variables out of there. So since I have P1 V1 equals P2 V2, making sure that I know which variables belong to the one and which belong to the new scenario is an important part of the question, which is why I was trying to point out there's that period there to tell me here's one scenario, and then there's a second scenario. So making sure that you've got that reading comprehension to read through what's happening and what's changing. From here, all I do is plug things in. I do want to double check that 15 is still in liters, so nothing changed to milliliters. And I'm going to assume my new pressure wants to be in atmospheres. I'm usually a little bit better about exams to make sure that those are all the same. So my P1 is going to be my 4 atmospheres. My V1 is going to be my 27.1 liters. My P2 is the thing that I'm looking for. And my V2 is my 15 liters. Now, we can go ahead and plug this all in, but the other thing to think about, I'm just going to plug things into my calculator for a minute. Sometimes I like to think that I can write and talk at the same time, and sometimes I'm like, no, let's just use the calculator for just a minute. 7 points. So my calculator gives me all of these digits. I don't want that many digits because on the exam we're going to do 3 sig figs. So 7.23 atmospheres. One of the things you always want to do in a gas law problem is make sure that the answer makes sense. Because the idea behind the gas laws is that what happens to one variable affects the others. So you should be able to have guessed which way the pressure should have gone from the question itself. So when I scroll back up, what I should have noticed is that I start off with a volume of 27.1 liters and I go to 15 liters. So I go from a large volume to a small volume. So my volume decreases. Anytime my volume decreases, what's happening is I had a certain number of gas particles that were zooming around. And then when my container gets smaller, those particles are still trying to zoom the same amount. And so they're going to bounce off the walls of the container a lot more often because of the smaller size. So since they're bouncing off the walls of the container more often, my pressure should actually go up. So my original pressure was 4 atmospheres. My new pressure that I solved for was 7.23. So the fact that my pressure went up from 4 to 7 is a good sign because my pressure should have gone up as my volume goes down. And this idea of the fact that as my volume goes down, my pressure goes up means that these two are inversely related. And keep in mind that that's another way that we can ask conceptual questions about gas laws is we can't just ask what happens to one variable as the other variable changes. So I have this note here. So what if this question was in torr? So we have a whole set of volumes and pressures. So what if this question, instead of being in atmospheres, what if everything was in a different pressure unit? We're also going to assume, so we're just going to cheat for a minute, and we're going to assume that the numbers are exactly the same. The only difference is that instead of ATM at the end, that was actually torr. So if my volume was still this 27.1 atmosphere or 27.1 liters, my pressure, instead of being 4 atmospheres, my pressure is now going to be 4 torr. My new volume, still 15. And we're going to assume that the new pressure, that we actually still wanted that to be in torr. So one of the interesting things about this particular equation is that because the way we would go from atmospheres to torr is by multiplication and division, means that this equation, as long as the units match, it doesn't matter what they are in. So as long as the units for P1, V1 equals P2, V2 are the same, whatever I put into it is what I'm going to get out of it. So I could do the exact same math, putting in my liters and my pressure, only now I'm in torr, is equal to my 15 liters and my second pressure. And again, You get the same answer. And now the only difference is that now it's in torr. So if you've never tried this before, where looking at which units matter and which units don't matter, it's if the units change because of multiplication and division, and your entire equation is multiplication and division, essentially all you would be doing is dividing the same number by both sides, on both sides. So whatever you get into it is what you get out of it. And in this particular case, you don't actually have to change those units. And why, yes, I do have one that will show you where that would change, where it would be different. But P1V1 equals P2V2, pressure units, volume units, you don't have to change. But just keep in mind that whatever you put in is the same thing that you'll get out. We actually saw that same idea back in chapter 9. I keep referencing chapter 9. When we did M1V1 equals M2V2, there was the same idea actually in this equation, that whatever units you put in were the same units you got out. So you could actually put milliliters into your volume in this equation, and you would just get milliliters out, and everything worked out just fine. So same general idea. Questions so far?
Yes, there's been one. Someone was a bit confused on the new Alex change. So if we finished all topics on time, it is 100. I do not need to go back and finish the precious topics for pi completion after it went down in objective knowledge check for the pi completion.
So from the sounds of that, hold on. Do I have a screenshot of the thing I want? Nope, I don't know what I want. Okay, so here's the deal with Alex. Because the thing is that here's the other thing I'm worried about from the sounds of that question. So when you look at Alex, there are two different things that you can look at. There's gradebook and there's assignment. Why on earth you have both of these is personally beyond me. Maybe Dr. Diekman knows, but I don't. They look almost identical, and for that reason are very confusing. The thing that says gradebook is the thing that we actually use for your grades. So if you're trying to figure out if you're done with Alex, one way that you could be done with Alex is if you have 12 objectives with grades that you like. They don't have to be 100. It's your life. They're your grades. I don't care what they are. Your life, your grades. 12 objectives with grades you like. That's what I'm going to say. Hundreds would be great, but 12 objectives with grades that you like. Because what we are going to do is one of the options is we're going to take the highest 12 of 13 objectives and have that be your Alex score. So that's option A. Is from the gradebook, taking the 12 highest objectives and taking your entire Alex grade, which is 15% of your final grade, the best 12 of the 13 objectives. That's one. The other one is pi completion. This is taking however many topics you finish. And by topics finished, this is actually topics that are learned plus the topics that are mastered. And we're going to divide those by your total topics. And whatever that is, times 100%, will be your Alex grade. Which one of these it is, what we will do at the end of the semester is we will calculate both, and we will automatically take the highest. There is no opt-in procedure. We just assume you want the higher grade. So, should I say A or B? A or B. So we will automatically take the higher grade of A or B. So whichever one is higher, that's the one that we'll take. The reason why I went ahead and stopped and talked about Alex was because I forgot about the confusion about the fact that Alex has this weird thing that says assignments. Honest to goodness, just don't ever look at that tab. It's my personal advice. If you're super curious about what assignment is, then show up to my office hours tomorrow at 4 o'clock and I'll explain to you what the assignment thing is. But the assignment is not where your grade's going to come from. Let's put it that way. So your two options are either from the gradebook, from your gradebook grades, or from your Pi completion, which usually your Pi is part of your home screen for Alex. And we will automatically take the higher of the two numbers. So usually in e-learning, you will see both numbers and we will automatically take the higher one. Again, there's no opt-in procedure. You do not have to email us and tell us that you calculated it yourself and what that is. We will calculate them both. We will automatically take the higher score. Other questions?
There is nothing. Oh, never mind.
There is one more question. Somebody is asking, when asking for TOR, couldn't you multiply 760 by 7.23?
So then it would be a different question. So the question is, so I rewrote the question. I assumed that we had a completely different question and I rewrote the question. So if you would like to rewrite the question again and say that you are given 7.23 atmospheres, what is this in torr? Then you have a different question from the one I was solving. So then at that point, then yes, what you have is for every 1 atmosphere, you have 760 torr. And then yes, you do the calculation as was mentioned. My point was more about how units in that particular equation worked. So I was trying to make a different point than what's being pointed out now. But yes, if the question was how do we go from atmospheres to torr, this is the way we do that. Or 5.49 E3. For scientific notation. So my apologies that was unclear, but I was essentially trying to do a completely different question. So doing another completely different question, here's how you go from atmospheres to torr. So yeah, my point before was to redo the question as if the entire thing was in torr, not changing in between. If you need to change in between, then you need to do a conversion factor. But my point earlier was the fact that if you were given torr and you wanted torr, you could just leave everything in torr. That's part of how P1V1 equals P2V2 works. Is if you have torr already, you can just leave it in torr. So that's what I was doing. So brand new different question if you want to go in between the two of them. So before I was either in atmospheres and staying in atmospheres, or I was in TOR and staying in TOR. Out of the chat, then someone's asking, how do we go in between them? And this is how you go in between them. So again, this was supposed to be a completely different question. So this one in blue was supposed to be a new question. New question, different set. Other questions?
Nothing at this time.
Okay. So continuing to skip around. If the skipping around annoys you guys can ask questions. I was trying to poke people a little bit. All right, so write the delta H of formation. A little standard symbol would have been great, but I forgot to find that in OneNote. You'll see later when I have some temperatures, there's no degree symbols in those either. Or the delta H formation reaction for carbon monoxide. So it doesn't actually give me it tells me that's a gas, that's lovely. But this is for carbon monoxide as a gas. So delta H of formation reactions, these state something really specifically, which is that I'm supposed to produce 1 mole of whatever it tells me. So this thing in the product must be 1 mole. It's part of the definition. And then I have to make that from elements in their standard state. So that's going to be carbon and oxygen, but I need carbon and oxygen in their standard states. So carbon in its standard state is actually going to be carbon as graphite. We would typically give you options of carbon as graphite or carbon as diamond would be your other option. But this thing is rare and is not the standard thing. So diamond is your other option, but it's the wrong option. And that should be a solid. And then my oxygen should be diatomic and a gas. Now this reaction does need to be balanced, and I have to keep my product as 1 mole. I have to. It's part of the definition of a standard enthalpy of formation reaction. So this actually gets the 1/2 symbol to make everything balance out. You should remember that there are 7 elements that are diatomic at room temperature. And I remember it from that acronym Brinkelhoff. So it's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Out of these, in case you're curious, this is actually a liquid, and this is actually a solid at room temperature. The rest of these guys are all gases. But all of these are diatomic. So let's put little 2s by all of them. So all of these are diatomic at room temperature, 1 atmosphere. So, and there's different ways to remember which ones these are. So if you have a different way to remember them, that's great. If you're curious as to when we talked about these, we talked about those back in chapter 5, by the way. So it's been a while since we actually taught you that information, but mention it, we did, and we're using it this time. So now is when we actually need to know that. So this kind of question where it's asking about the delta H of formation reaction for something specific, usually this is one of those multiple choice questions where there's a whole bunch of different reactions, and you have to pick out the correct one. One of the things, every time I talk about this, I don't have it anywhere remotely close to me. One of the things that I've talked with some people about is trying to use something like sticky notes on your monitor. I'm trying desperately to find a sticky note, but I guess I will just use the sticker. So if this is, my mother's texting me. So if this is my computer screen, and I should then have basically a sticky note that would let me very slowly move in between everything on my screen so that I could basically keep track of what was going on and which one was which. So the whole notion of trying to use a sticky note to keep track of line by line what's going on. So some of your incorrect answers would have information like this, where we would have carbon as a diamond plus 1/2 of your O2 as a gas goes to this as a gas. This one is wrong because of the diamond. So this is a wrong answer. We would also have options like, here's my graphite that's back. And then we would just have the one oxygen by itself. Go ahead and tell you that's a gas, solid. This is, well, would really help if I kept to carbon monoxide like I'm supposed to. This one is wrong because of the oxygen. So the oxygen should be diatomic. So anything that's not diatomic oxygen would be incorrect. We also usually do one that is balanced incorrectly. So maybe it's got the O2 and everything looks pretty good, but then there's actually a 2 here and a 2 here. And this one is wrong because it has to be 1 mole of the product. So this is the kind of question where you just kind of take a deep breath, and I would recommend that you write out what you're looking for on your scrap piece of paper so that you know what pieces you want, because this is another one of those questions where all of the answers start to look the same the more you look at them. So take a deep breath and write down what you want and then go try to find it, because it's not conceptually, the question's not that bad. This one is almost just worse when you're faced with the multiple choice options, because then you've got to figure out, what do I actually want? Because now suddenly everything looks good. Yes.
We have somebody asking, do we always separate the product into its elemental reactants, or there are exceptions like polyatomic ions? Also, how do we know the state of the reactant?
Okay, so this is for something very specific, which is for delta H of formation reactions. So this is not for all your delta H reactions. This is just delta H of formation. So I know it's really small on the screen, but there's a little tiny F down here, and that F stands for formation. So everything that we were just talking about is specific for delta H of formation reactions. So that little tiny F is all about formation. So that's what guides everything we were just doing. So if in fact we were trying to do something that was polyatomic, so let's say we were trying to do sodium, I gotta think, I'm gonna keep it with some elements like what we were just doing. Here's sodium carbonate. So we've already talked about the fact that my oxygen is a gas, that my carbon should be graphite as a solid, and then the only one we'll have to add is our sodium, which is solid. As far as how you know things like which what things should be as far as which states of matter, so this is something where honestly, we think you guys remembered stuff and learned about different elements from high school or other times. So when you look at a periodic table, there are some things we assume that you know. So like I just mentioned, these guys, I guess we can include, no, we don't know what that is. So all of these are gases. There aren't that many liquids on the periodic table. Oh, crap, I lost chlorine. And chlorine. Chlorine's also a gas. I gotta redo that. So nitrogen, chlorine, all my noble gases, those are all gases. The only two things I assume people remember are liquids are mercury and bromine. So there's only two liquids to worry about. Liquids, which is mercury and bromine, and the rest of your periodic table are solids. So how are you going to know what state things go in? Most of your periodic table are solids. Sodium, metal, it's a metal, it's solid, just like copper metal, just like iron metal, they're actually all solids. Your noble gases are gases. That shouldn't be a surprise. Bromine being a liquid may be new information. If it's new information, now you know. Bromine and mercury are both liquids. There simply are not that many on the periodic table. Otherwise, most of what we're going to be looking at are things, like I mentioned before, the 7 diatomic elements that are naturally occurring diatomics, that Brinkelhoff, that you need to know. But otherwise, those are the things you need to know for those standard reactions of formation. And again, those standard enthalpies of formation reactions are a specific concept. So I know that that little f is really small, but that's when this comes into play. So even if it's a polyatomic ion, I didn't balance this yet. Even if it's a polyatomic ion, 2, one of those, 3 halves. Even if it's a polyatomic ion, you still represent that the same way. This is a, we'll pretend that this is a solid. Why not? That can be a rock. It's a solid, it's a salt. So delta, so standard enthalpies of formation reactions are a little bit funky because you do have to keep track of everything, but it comes from elements in their standard states. So that's where it comes from. Okay. Other things so far?
There was one more question of, is STP the same as the standard state?
No. So this is the only, STP is the only thing that's bad about putting gases and thermodynamics together. Because in thermodynamics, which is the fancy name for chapter 10, whenever we're talking about standard, we are talking about 1 atmosphere of pressure, and we're talking about room temperature, 25 degrees Celsius, which is roughly room temperature. Where humans are comfortable. Where humans are comfortable. In gases, this is actually a really good question, by the way. There's something that's we just refer to as STP, which is standard temperature and pressure. And someone needs to ask Dr. Seibert why these two things are different, because I do not know off the top of my head. It's got to be a historical thing. I'm confident Dr. Seibert knows the answer off the top of his head. I do not. And STP for gases is 1 atmosphere. That's my pressure. And 0 degrees Celsius, or 273.15 Kelvin. So the pressure is the same, but the temperature is different. So gases at STP have a completely different temperature assumption than in thermodynamics. By the way, physicists will occasionally make fun of chemists because of this. And honestly, it's the one time when I don't blame the physicists for making fun of the chemists, because why wouldn't you want to be humans to be comfortable? I don't really know. Because thermodynamics, you assume the human beings are comfortable and sitting at room temperature, and in gases, you assume that the human beings are cold for wearing jackets, because it's 0 degrees Celsius, and I'm cold. It's 0 degrees Celsius. I'm alive, but I'm cold. Other questions?
Yeah, there's one more. It says, so when asked formation questions and not given an equation, we have to do this method of creating one using standard states. We would use the table of enthalpy formations if asked for delta H for these.
Oh, okay. So I think that the person's asking what you do with a delta H of formation. So I was talking about what they are and conceptually how you would make their reaction, but there is then a way to use a delta H of formation. So let's go ahead and take a look at one of those. This one. See. Let's make this a bit bigger to make our lives easier. Oh, no. I want 8 font size larger. There we go. Okay. Calculate the enthalpy of reaction for the following using standard enthalpies of formation. So granted, I mentioned earlier I was having problems, but this should, in this table, have a delta H like this to tell me that that's what these are. But it does say standard enthalpies of formation in the question. So we were just talking about what those look like. Now here is a table with a bunch of that information. And so it says calculate the enthalpy of reaction for the following reaction using standard enthalpies of reaction. So essentially, it's not asking us what these all look like. This is just now using them. So granted, we don't really care, but to piggyback off of what we were just doing, if I wanted to say, hey, we're forming C4H10 as a gas, this would come from H2 as a gas and carbon as graphite as a solid. I would need 4 carbons. I would need 5 hydrogen gases to get C4H10. And so this reaction is what actually has that value of delta H in the table. So whenever you see this table, they're going to leave out these particular equations because these equations are part of their definition. So they're going to assume that you would just be able to figure out that equation. But this equation is what's describing that negative 124.7 kilojoules per mole. So if we have this reaction and we have this table of delta H of formation values, in order to actually figure out my delta H of reaction, I change an enthalpy of reaction. What I'm going to do is I'm going to use this table, but I'm going to take the sum of all my products minus the sum of all of my reactants. That is essentially, to figure out the change, I'm looking at final minus initial. I don't remember the last time we talked about it, but in my class, I'll try to point out every time that we're just using final minus initial to get the change. So because it comes up a fair number of times in chemistry where we're really just using final minus initial. And that's all we're using here, is we're using final minus initial. So in order to do this, I need all of my final stuff, all of my products. So I have all of my products. There's 8 carbon dioxides as a gas. So carbon dioxide, they gave me 2 carbon dioxides. I just want the one of a gas. So that's this guy here. So it's 8 times negative 393.5 plus 10 waters. My water is, oh, they only gave me 1 water. That makes my life a little easier, negative 285.8. So that's all of my products minus all of my reactants. They gave me multiple carbon things. That's lovely. So 2 times negative 124.7 plus 9 times oxygen as a gas, that's 0. Anything that is in its standard state, so this is an element in its standard state, that delta H of formation value is equal to 0. And you will not find it in the table that we give you. I should actually say you'll not find it in the table that we give you. It is actually in Appendix 2 in your textbook. Did Alex time me out? No, didn't. Aha. Oh, darn. Well, I was going to try to show you Appendix 2 in the textbook. Maybe I still can. Maybe. Maybe not. So granted, it's a lot faster looking at me struggling to do this if you just know that your standard, that anything in its standard state is 0. Also, they give you a lot of information, but part of what they give you is a standard enthalpy of formation, so that we've been talking about the whole time. They also give you this delta G stuff and S stuff, and we won't talk about delta G or S until Gen Chem 2. So for those of you waiting to talk about Gibbs free energy or entropy, you'll be waiting for a while. I think that comes in early April. But anyway, you can see 0 at random intervals. So here's carbon as graphite, which we've already mentioned is in its standard state, and that's a 0 enthalpy of formation. The scrolling probably hurts your eyes. It kind of hurts mine a little bit, so I'm going to stop scrolling. But anyway, if you're curious, you can go to Appendix 2, which gives you thermodynamic data at 1 atmosphere and 25 degrees Celsius. But it's a lot faster if you know off the top of your head that an element in its standard state has a delta H of formation value of 0. Much faster. Now, this is where you're going to watch me walk through this really slowly. Oh, the sun goes down faster. Not faster, sooner. What is that? 393.5. I have to make sure that I actually put all my numbers in correctly. Because one of the places where people often mess up, myself included, is by putting in the numbers too quickly. 10, that makes my life easier. Plus negative 2,858. So oftentimes the problem with these delta H of formation problems is not in the mathematics of the concept, it's oftentimes in dealing with negative signs. So whatever way you like to keep track of negative signs, make sure you do it to the best of your ability, because this is usually where people have problems, is just in keeping track of the negative signs. So this is negative 6,006, and this is minus a negative, which is technically adding 249.4 plus 249.4. equals negative. I shouldn't be too surprised. I'm burning a hydrocarbon. This had better get me some energy out. My entire table is in kilojoules per mole, so that's still the unit that I'm in. I want to do this in an exam format, which would be 3 sig figs. So my enthalpy of my reaction, since this is dealing with enthalpy, I should have that negative sign involved here. I only want 3 sig figs, 5 point, we'll just assume we're doing some standard in scientific notation. 5.76E3. So making sure you're happy with all of your negative signs always seems like the least little thing to worry about because there are so many concepts in this section. But for that reason, by the time you've gotten all your concepts right and you figured out what you're supposed to do, making sure that you're getting those negative signs in there correctly, very important thing to do. So don't lose track of those negative signs as you go through. Now, I actually did this question to try to answer someone's question. So hopefully that actually cleared up the question that was asked last, because that's actually why I went down this tangent. How are we doing on questions?
We don't have anything at the moment.
Okay. So I did that one. I want to do this one. But note about Kelvin is to myself. So if those being like, she deleted something, I did delete something. I deleted the note to myself. Okay. A balloon, which we are going to define as being a perfectly elastic container, is filled to 22.4 liters with argon gas at 25 degrees Celsius. See, that's where my degree symbol, I couldn't find it. Degree symbol. The temperature drops to -4 degrees Celsius. What is the new volume of the balloon? Assume pressure is constant. So again, I am going to go ahead and do my trick because I do not have all my individual gas laws memorized. So I put everything equal, PV divided by NT. 1 is equal to P2 V2 divided by N2 T2. And what do I want? I have 22.4 liters. That's the volume. And I have 25 degrees Celsius. That's the temperature. And then the temperature drops. That tells me there's a change to -4 degrees Celsius. What is the new volume of the balloon? And it tells me that I can assume pressure is constant. So I definitely don't want pressure. And I'm in a balloon that I'm going to assume is keeping all my moles of gas. So I don't want those either. So the only thing I'm left with is V1 T1 equals V2 T2. Now, the reason why I wanted to make sure that we did this one, and I actually picked these numbers mindfully as well, is to point out the fact that since we are dealing again with gases, so we're back to there's no more enthalpy values, there's no, there is a temperature, there's a temperature change, but this is argon gas and dealing with volume. So we are back, we flipped back now to chapter 11. Realize that if I just plug things in as they are in Celsius, I would actually get a negative answer for my volume. So this is the reason why when you're dealing with temperature in chapter 11, dealing with temperature and gases, you have to always use Kelvin. So with gases. I don't care what you're doing. You have to always use Kelvin when you're dealing with gases, because the thing is that Kelvin is the only temperature scale that's going to let us actually use temperature to interact well with things like energy in a way that makes sense. Kelvin, you can actually say this is twice as much as that if you're using Kelvin. Celsius doesn't really work that way. You can't really have going from 10 degrees Celsius to 20 degrees Celsius isn't really twice as hot because the 0 of Celsius is not super useful. So this is 298.15 Kelvin, 98 Kelvin, and this is 269.15 Kelvin. So we have to have Kelvin in order to deal with temperature in gases. It's really tempting sometimes to use Celsius, but you need to always use Kelvin when you're dealing with gases. So my volume, so now I can go ahead and solve my problem. So 22.4 liters divided by my 298.15 Kelvin is equal to a volume that I don't know yet, divided by 269.15 Kelvin. And then I can solve. For those of you who are curious, this is technically Charles' law times 269.15. And oh, I meant to do it and I forgot. So before I actually put up the number, when we talk about what's happening here, my volume, my temperature is going down. And when I talk about the fact that my temperature is going down, my volume should also go down. So essentially, with a perfectly elastic container, as temperature decreases, my volume also decreases. This is the reason why when we have a cold snap, you need to check your tires, because your tires will deflate, not necessarily deflate, your tires will shrink. That's a little bit, which is bad. So every time the temperature goes down, your tires will also shrink a little bit, will get smaller. So temperature goes down, volume goes down. So when I look at my final number, my temperature went down, so my volume should get smaller. My volume was 22.4 liters. My new volume is 20.2 liters. So it went in the right direction. So this is one of those things, again, just to be aware of as you're going through, that there's a relationship between all of the variables in the ideal gas equation. So you should be able to predict what's going to happen with your gases. So always use Kelvin with gases, and make sure that you can kind of predict what should be happening. My temperature is going down, my volume should also go down. And yeah, always use Kelvin with gases. The other way that you know that you've got to use Kelvin, by the way, because before we talked about torr and it was like, it's fine. This addition thing, the fact that you change between Kelvin and Celsius with addition is part of the other reason why things don't work quite as well as you'd like them to. So always use Kelvin with gases. I don't care what you're doing. I don't care if it's Charles' law. I don't care if it's in the ideal gas equation. I don't care where it is. If you're doing gases, you're going to use Kelvin. We'll give you Celsius a lot, by the way, but if you're dealing with gases, you always need to be in Kelvin. Questions on this one? I'm gonna guess not. So what else do I have? This one's nice and short.
We have a question.
Oh,
Somebody's asking, what does it mean by perfectly elastic container?
Oh, so the perfectly elastic container That really is just to tell you that you don't have to worry about it, essentially. So for example, I mentioned tires, right? Tires on your car. So a perfectly elastic container, something that's going to happen with a perfectly elastic container is it's going to move and change volume easily.
There is also one more question. Do we need to know the name of each of the equation like Charles' law or Boyle's law, or just the concept of direct proportionality or indirect proportionality?
So as far as knowing the names for all of the gas laws, this is one of those times where you guys have an open book, open note exam. You should know them, or you should at least have it written down in your notes somewhere so that you could find that information. In previous years, I confidently would have given you a different answer, but this is the year that you guys have access to your notes while you take the exam. So I would not feel bad at all about asking you something about Boyle's law or Charles' law or Avogadro's law, because you have an open book, open note exam. So I'm going to go ahead and tell you to know that. If your individual instructors tell you something different, then by all means, that's fine. But I'm going to go ahead and say it's an open book, open note exam. And gosh, it should be really easy to have that written down in your notes. Yeah, so the perfectly elastic container, a lot of times that's just language to basically cover our bases. So in real life, the fact is that these don't usually exist. So a moment to talk about real life, and talk about the tires on your car. So this is a car. Windshields. Person. That is a very small person in a very large car. It's fine. It's fine. So your tires are not perfectly elastic. So I was mentioning the fact that when you have a cold snap, your tires usually get a little bit smaller because the volume decreases. That is true, by the way. That is true. But the thing is that when you're looking at your tires, usually the temperature goes down, the volume goes down, and the way you actually figure that out is by checking the tire pressure. And that's because your tires are not perfectly elastic, which is a good thing, by the way. Your tires are rigid enough that your tires will maintain their shape somewhat without that gas helping blow them all the way up. They'll change shape because of the change in temperature, but the pressure also goes down if there's not when the temperature changes, because they're a bit rigid. So tires are kind of awkward because they're not perfectly elastic, not perfectly elastic in real life, but they're bendy. So usually your tires should be kind of like nice and flat on the road and look like rectangles. And when it's cold outside, they tend to like bow in a little bit. This is exaggerated, by the way. But when it's cold outside, your tires will actually shrink this little bit. And essentially you're not getting as good of traction on the road because the middle part of your tire is not connecting with the road like it's supposed to. So this is why we care about tire pressure. And in case this is cold. When it gets hot outside, then you get the opposite shape because they blow up a little bit. Hot. And this is low pressure, high pressure. So that's why you gotta check your tire pressure in Texas when you get a cold snap or when it suddenly gets warmer outside, because you want your tires to make the correct amount of connection with the road. But yeah, your tires in real life, not perfectly elastic. So in real life, things are more complicated. So a lot of times in problems, when we don't want you to care about extra stuff, we say things like perfectly elastic. Anytime we have extra words in problems, a lot of times we're trying to tell you to not worry about something and just be like, it's fine. Or the balloon. Balloons are actually pretty much perfectly elastic. They work great. Most things don't. Balloons do. Balloons are fine. Balloons are wonderful. So, or sometimes you'll see we'll do a problem about a tire because we're tired of talking about balloons, and then we tell you that it's perfectly elastic tires because they're magical tires, apparently. So, different wording we have just to try to tell you that the volume will change easily. That's all it's for. I rambled a lot. Did I answer the questions?
Yeah, I think.
Okay.
We
Excellent.
don't have any more questions at the moment, though.
Fabulous. Oh, I was going to do this problem next. While we're talking about gases. So, as I've mentioned before, I will never be able to talk about all of the things. But I wanted to go ahead and bring up this one because oftentimes people are like, okay, so as long as I know PV equals nRT, I can do all of the math out of chapter 11, right? Here's the part where you would be incorrect. So this says a gas cylinder has 2 moles nitrogen gas and 2 moles oxygen gas. What is the partial pressure of nitrogen in the gas cylinder? Partial pressure. So all we're saying is that you've got a gas cylinder. Everything I draw is rectangles. I do not have great drawing abilities. And we have some nitrogen gas. And we have some oxygen gas. And all I want to know is about the nitrogen. I don't care about the oxygen. I would like to pretend like the oxygen is not there at all. In order to do this, then, I'm going to need one more piece of information that I forgot to put in this problem because I got distracted. Assuming, pardon me, the total pressure is 1 atm. Make my life easy. Okay. Sorry, suddenly realized that I wrote this question poorly because I need more information to solve it. So this whole notion of partial pressure is the idea that you could talk about just one thing. So oftentimes this actually comes up when we talk about things like the gases that we breathe or the partial pressure of oxygen in our lungs because we need a certain amount of oxygen so that we can breathe. So a lot of times it comes up in that regard. So this is more of a contrived problem to deal with it. But the other thing it has is it has moles and I want pressure. So what we're going to do is we are actually going to use something called mole fraction because it turns out that the mole fraction of a gas is going to be equal to the partial pressure of that gas divided by the total pressure of that gas of the gases. Mole fraction is just the fraction of that gas. So in this case, we're going to have, we care about nitrogen. So 2 moles divided by total, which in this case is 2 plus 4. So my mole fraction, which is supposed to be the Greek letter chi, by the way, that's why I'm drawing this really funky looking X, is if I was doing this well, it would be the Greek letter chi. I don't do things super well, so it looks like a bizarre cursive-ish X. I'm going to leave that as 1/3 for right now. So 1/3 is equal to the pressure of the gas I'm interested in divided by the total. For the partial pressure of the gas I'm interested in, which is just nitrogen, so I could go ahead and say nitrogen. My total pressure, I already found out, is 1 atmosphere. And I now know that that's equal to 1/3. So I can go ahead and multiply my 1 atmosphere by both sides, I get the partial pressure of nitrogen to be 1/3, or we can go ahead and plug that into our calculator to know that that's going to be 0.333 atmospheres. So if you have not gotten to this section yet, the main reason I wanted to bring this up again was because a lot of times people are like, oh, as long as I know PV equals nRT, I got all the calculations. And that's not true because of this little tiny thing known as partial pressures. And partial pressures are also equal to our mole fraction. So there's a couple of different ways that partial pressures can come up. So do make certain that you're still kind of keeping your eyes out for different calculations that can come up, because there is more than just PV equals nRT in the gases chapter. And then it is a little bit more information dealing with how we can work with partial pressures. This, by the way, partial pressures is one of the things that will come back in Gen Chem 2. So this is one of the oddball bits of information that will come back in chapter 2 in January. So this one will actually come back and will come back early. So I understand that we're going to have like winter break in between these. So don't worry, we'll refresh about it then too. But partial pressures are one of those kind of odd things that are towards the end of chapter 11. Still involve calculations, a little bit heavier on concepts, because you've got to know what to do and how things relate to each other. This also usually comes up with things like Dalton's law of partial pressures. All that really means is you get to add them together. So sometimes you'll have something else. This is actually my favorite question because it always looks really like, oh no, what's going to happen? So sometimes it'll say something like this. A container. You can make up your own kind of container. A container has 0.1 atmospheres of N2, 0.3 atmospheres O2. These should all be gases, by the way. Me leaving out my state symbols again. And 0.4 atmospheres hydrogen. What is the total pressure? This always looks like, oh no, I have to do something really complicated. You don't. Total pressure, you just add them all together. So this actually really is just 1.1 plus 0.3 plus 0.4 is your total pressure. And I realize we need 3 sig figs. Oh, bother. 3 sig figs. But essentially it is. Partial pressures are all about the idea that you just add them together. So partial pressure always sounds really fancy, and sometimes it can be. There are fancy ways to use partial pressure. The mole fraction was fancy-ish. But usually when we start out, we're just like, and you add them together. Ta-da! So partial pressures, personally, I consider to be more conceptual, because anytime we get to add or subtract, usually that triggers like a, are we allowed to do that? And the answer is yes. And usually that confidence that yes, all we're going to do is add them together comes from understanding the concept of partial pressures, where all we're doing is saying, sure, we have a whole bunch of different gases, and if we wanted to, we could talk about the contribution of each individual gas, if we wanted to. And again, this is valuable in real life when we talk about, is the partial pressure of oxygen high enough that human beings can breathe? Or fish, sometimes also a good thing. Fish do breathe oxygen, by the way, in case you didn't know. They don't have lungs, but they do breathe oxygen out of the water. Again, more of a Gen Chem 2 thing. But. I'm going to switch topics. Again, unless people have questions about partial pressures. Partial pressures are one of my favorites because they're just kind of strange, but not bad once you accept the fact that you get to add them together. And it kind of makes sense that we've got nitrogen and oxygen and a bunch of other gases hanging around, and we could just talk about them by themselves. But we don't usually do that. So it's like, are we allowed to do that? We are totally allowed to do that. So I want to make sure I have enough time to talk about this one. So I need to close OneNote and reopen it. Oh, no, I think it's okay. All right. There we go. Didn't select all of them. No. Okay. Sorry, every once in a while I learn more about OneNote. I'm like, oh no, did I mess everything up? I believe the answer is no. There we go. Calculate the enthalpy of reaction. Hey, we're back to enthalpy. We're back to enthalpy. For the following reaction using bond enthalpies. What? Bond enthalpies. So, hey, look, we have different information. These are also in kilojoules per mole. But now these are bond enthalpies. So when you have, oh crap, and I meant to draw this out too. So if this was the exam, by the way, we would have actually written out C4H10 for you. Hopefully better than that, but at least we would have done that. Really, we probably would have, mostly because there's two different ways to draw this. And so we should have at least told you if it was in a chain or if it was not in a chain to make certain that we covered that no one's worried about how many kinds of different bonds there are. So I think you actually be this. No, it doesn't matter. I am not going to try to think through if it's the same no matter how we draw this. So with bond enthalpies, the main assumption is that we are taking our reactants and we are going to take every single bond in our reactants and we are going to rip them all apart. And we are going to go to individual atoms. I have to draw 9 O2 molecules, don't I? Yay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 6. Okay, good. So we are taking all of these, absolutely all of these. And we are going to rip them into individual atoms. They are not happy as individual atoms, by the way. Unhappy. This is not a good state for them to be in. They don't like it. There's a reason why O2, why oxygen is diatomic at room temperature. It likes being diatomic. Oxygen doesn't want to be monatomic. It doesn't want to be by itself. It's the whole reason it forms bonds. Carbon loves forming bonds. That's the whole reason carbon-based life, it's such a good thing. Carbon bonding, it's awesome. Individual atoms? You're going to make carbon be alone? Blah, no. So the whole reason I'm making this big dramatic deal about this is that to go to individual atoms, this is going to require energy to go to individual atoms. So everything in the reactant side is going to be positive because it's going to require energy. Anything that requires energy is going to be an endothermic reaction, ripping bonds apart, making them unhappy is going to require energy. So all of the bonds, my 9 oxygen-oxygen bonds, my 9 oxygen-oxygen double bonds, and my, oh man, sorry, it sounded like I have to count all these. So there's, oh, all of my hydrogens are connected to carbons. There's a shocker. I have 20 hydrogens because there's 10 on the first molecule and 10 on the second molecule. So I have 20 carbon-hydrogen bonds, and I have 1, 2, 3, but there's 2 of them, that's 6. I have 6 carbon-carbon bonds. So all of this stuff we are ripping apart. Because I'm ripping it all apart, it's positive. So this is going to be endothermic. So I rip apart my reactants. So my reactants get the positive symbol because it's endothermic. I rip them all apart. So I drew out all my Lewis structures, and there's a lovely table. We'll work with that table in just a minute, but I'm not done yet. Then I'm going to form all of my products. So I'm going to form my products. I'm going to make bonds. I'm going to let things go from individual atoms to being back together again. This is way more stable. So this is actually going to release energy. So I'm going to make 8 carbon dioxides. I am leaving out the lone pairs because otherwise I'm going to be here forever. So, but the reaction says 8 carbon dioxides. I am now realizing why in class we usually use like methane, because I don't have to draw so much. So since we're forming, and this is going to release energy, everything on my product side gets a negative sign. There's 8 carbon dioxides. For every 1 carbon dioxide, I have 2 carbon-oxygen bonds. So that's going to be 16 carbon-oxygen double bonds. And the other thing I have is I'm going to have water. How many waters do I have? 10. 10 waters. So same idea. 1, 2, 3, 4, 5. Yes, I'm going to draw them all out. I realize some of you are sitting there and you're like, I can already figure out that it's 20 oxygen-hydrogen bonds. I really can. But I'm going to sit here and draw these. So that way we have drawn them all out to make the point about where bond enthalpies are coming from. We are forming all of the bonds. We rip them all apart in the reactants and we form them all in the products. 20 oxygen hydrogen bonds. This part's negative because it's exothermic bond forming. That is our products. So endothermic bond breaking. So bond breaking is endothermic. Those are our reactants. Bond forming is exothermic. Those are our products. All we have to do now is put the numbers from the table in there and we'll be done. So my 6 times my carbon-carbon bond, that's 347. So 6 times 347 plus 20 times my carbon-hydrogen bond. Yes, I have to scroll back up for the table every single time because I don't have those memorized. We will give you this table. We'll give you some version of this table. 498. So 347, 414, 498.7 minus 16 times carbon-oxygen double bond, 745 45 plus 20 OH 460. Okay. So close to being done. Yes, I am going to keep writing things down because we're back to that whole positive negative thing again to make sure I don't mess up. 2082. Come on, OneNote. There's always that time where OneNote tries to not help me very much. 4 times 20. 0 plus 9 times 4, 98.7. 4488.3. And yes, I'm going to keep everything, I'm trying to keep everything color coded. On 1920 plus, that's 460. No, it's okay, it's okay, it's okay. I'm going to finish this problem, even though OneNote's not saving my work, it'll be okay. So yes, these problems can be a little bit long. Yes, I know I made it longer because I wrote everything out. One, 2, 0. 148 plus 0.3. Negative 6,269.7. Yep, okay. 21,000, 14,000, okay. And yes, we can do delta H of the reaction, 3 sig figs, 6.30 E3. I'm actually take a screenshot of this because OneNote's not going to hold it for me. So a screenshot will help me out later. I'll have to deal with the fact that the 460 is off the page, but that's a different problem for later. And I would scroll up, except it's not going to let me. Maybe it finished syncing and it will let me. But the table should have been in kilojoules per mole. So as usual, we'll use whatever is on the table. Any questions on this one?
There is this one question that asks, on the exam, what steps do you suggest when doing bond enthalpy questions, like drawing the structure or any other tips?
So, hold on, I gotta get off of this. Oh, OneNote, hold on. This just happens to OneNote. It gets mad at me at some point. It wouldn't be an exam review if it didn't get mad at me somewhere down the line. That's okay, because I saved my work. So as far as tips on bond enthalpies go, the thing is that you usually have to draw out at least one of whatever you're doing. I know I was a bit extreme in the fact that I went ahead and wrote out all of my oxygens. The thing though is that you do have to draw your Lewis structures because we're going to have, I was nice and there's only enough information in this table of what you actually needed, but usually we're a little bit meaner than that. And we also will give you an oxygen-oxygen single bond and a carbon-oxygen single bond. So when it comes to things like carbon dioxide, you have to know if that's going to be a carbon-oxygen double bond or a carbon-oxygen single bond, because we'll give you the information for both. Same thing with your oxygen. You've got to know that that's a double bond in there. If we're doing something with nitrogen with N2, that is a triple bond in between there. It's supposed to be a nitrogen. So you are going to need to draw your Lewis structures. So the good news is that we typically don't ask a lot of bond enthalpy questions because it often takes you a little bit longer because you have to draw them out. But these are ones where, yes, you do have to draw them because usually we are mean enough to give you all of the options for a nitrogen-nitrogen bond, a single bond, a double bond, a triple bond, and you have to draw it out to figure out which one is which. So if Lewis structures are something that you haven't thought through in a while, it would behoove you to go back and draw just some relatively small ones. We won't deal with resonance on bond enthalpies because there's no half bonds in a bond enthalpy table. So that is at least one of the saving graces, is you won't have to deal with resonance because that's not going to be in the table. But otherwise, Lewis structures are back. They'll be relatively simple, but these, all the ones, the one with the 4 carbons, that one's a little bit hand wavy because there's multiple ways that those carbons can go together. But the oxygen's fine, the carbon dioxide's fine, the water's fine. Smaller carbon hydrogen things would be fine as well. Or again, we could help you in giving you the line angle formula. So this is helping because essentially we give you that is the structure. So realize that you might also want to go back and look at your line angle formulas, just because we could very well be like, oh yeah, so this is totally what the structure is. Ta-da, there it is, instead of drawing out all the carbons and hydrogens. That really just depends on who's writing that question as to what they want to do and how that's written out. The nice thing is that since it's all bonds, even though I have everything written as gases and liquids, you may notice that information is not in the table. So your bond enthalpy data is missing any information about state symbols because it's just a carbon-hydrogen bond. It's just a carbon-carbon bond. There's no information about what state of matter it's actually in. So good news, it's a little bit simpler as far as state symbols go. But yes, you do have to draw everything out. So it gets a little bit hairy for that reason. Other tips really is to just take a deep breath, because a lot of times with bond enthalpies, folks will sometimes get a little bit twisted between bond enthalpies and enthalpies of formation. That's actually the main reason why I chose to bounce back and forth between gases and thermodynamics today. So I understand that some folks probably didn't like the fact that I did a little bit of gases, I did a little bit of thermo, I had a little bit of gases, I did a little bit of thermo. Honestly, that was because I really do not like doing standard enthalpies of formation and bond enthalpies right next to each other. And it sometimes is very natural to compare the two, but it's the Sunday when we're all getting back from fall break, and I was a little bit worried that if I did those right next to each other, it would do more harm than good. So I tried to separate them a lot, because you do essentially wind up with reactants minus products in bond enthalpies, which is a little bit strange, different, but and it is. Do take heart at least that we know that this is the kind of problem that does take longer. So we know that, we're aware, and so therefore we will have it represented on the exam in a way that makes sense because we know it takes longer. So we're not going to have like half of the exam be bond enthalpies because you'd never finish. Same thing, like, I know it's been a while, but you may have noticed on the last exam, there weren't that many limiting reactant problems, right? Like, we asked you a limiting reactant problem. It was on there. There might have been 2 of them, but there really weren't that many limiting reactant problems because they take a long time. They're really involved problems. we can only ask so many because timing matters. Other questions?
Somebody's asking how many questions are there on the final exam?
On the final, oh gosh, I was supposed to work on that over fall break. So on the final, so just like all of your exams, where on your exams we have something that we're shooting for, right? So exam 5, which we're still working on writing, you're gonna look this somewhere between 27 questions to like 32 questions. I don't know where it's gonna be. That's a really big range. I don't know where it's gonna land. I'll know by Friday morning. Similarly, the final, that usually has somewhere in between 60 questions to 75 questions. So similarly, there's a range in there on the final as to how many there are. And yeah, and I don't actually know where that one's going to land either. Oh, it's going to be a busy 2 weeks, isn't it? So the thing to keep in mind for the final as well is that we are basically going to be trying to represent each one of the sections. So when it comes time to study for the final, let me go ahead and give you guys this advice. My classes have heard this, so if you're in my section, I'm sorry, it's a repeat. My biggest piece of advice for the final is, while yes, you do need to look back over your notes. Look back over notes is definitely something I want you to do. The first thing I actually want you to do is to go back over exams, the exams that you took this semester, and look at what you got right. Here's the reason. A lot of times there's stuff that you knew how to do. There are things you knew how to do back in September, and you'll remember how to do them again. It's just been a while. Like, there was a time that we did like wavelength to frequency calculations. There was a time we talked about protons, neutrons, and electrons. And you'll remember how to do a lot of that if you go back and refresh on it. But a lot of times folks focus on stuff that they got wrong. And it's good to look at that too, but that's not where I recommend you begin. Start with what you got right. Go back and remember things you used to know how to do. And then, in whatever time you have left, then look at stuff you got wrong. Also look back over your notes, mostly because there are going to be different questions. So there are different ways to ask the same question. And a lot of times, if you're just focused on this is the way they asked it in October, realize that we have the same set of authors, but we're all scrambled again. So you may see something written a different way. You may see a question asked in a different way. So if you're just focused on your exams and just your exams, you're maybe missing different ways we could ask that same question. So that's the other reason why I do recommend you guys look back over your notes as well, because that way you guys don't get tunnel vision just on the old exams. But do look at the old exams to look at what you got right. Yes, also look at stuff you got wrong, but start with what you got right because you knew a lot of stuff. Other questions, other things?
Somebody's also asking, would you say that this exam has more application questions or more rhetorical questions?
Since we haven't written it yet, and I haven't even written my questions yet, I couldn't say. It's a great question. Ask me on Friday. Ask me on Friday. I don't know right now. Other questions?
There's no other questions at this time. And we've just at 6 o'clock.
Yay! Excellent.
So thank you, Dr. Taylor, for
Absolutely.
putting this on as always. Students, this will be, we'll get this finished recording and put on our YouTube here shortly, hopefully. So
All right.
have a good night, y'all, and goodbye.
It's good. Bye.